All right, so let's finish up section 6.1. And we're going to talk about arc length. Okay, so arc length basically is the length of an arc if you draw an angle inside of a circle. Okay, like that. And you look at where the rays of the angle intersect the edges of the circle. That arc, that's what we're talking about. So in red, I've drawn an arc. Actually, a couple arcs. And the idea of arc length is that it's directly proportional to the size of the angle. Okay, basically what that means is if you take an angle and you double the size of this angle, you double the size of the intercepted arc. Right? If you take the angle and make it 1/3 as big, you make the intercepted arc 1/3 as big. Right? So that's directly proportional, meaning we can set up a proportion, okay, to solve arc length problems. So what we'll do is we'll set up a proportion and come up with a formula, and then we'll be able to just use that formula. All right, so what we need, though, is a kind of a fact to start off with. Okay, we have to know some kind of connection between angle size and arc size. So for example, if I said to you, I want you to convert feet to inches. Well, you've got to start off with a conversion. You've got to already know something. Like if you have a certain amount of feet, it's a certain amount of inches. So a conversion a lot of people use, if you have 12 inches, there's 1 foot. Right? And you can use that to convert any number of feet to inches or inches to feet. Just because we're using a 12 and a 1, does that limit you in any way to what, could you work with 72 feet if I asked you to? Yeah. And convert that to inches? Yeah. So just because you pick 12 and 1, you're not limited to what you can convert. Right. So what we're going to do now is try to come up with that connection. Okay? Just like we had between feet and inches, except this is going to be between radians and arc length. Okay? Or angle size and arc length. So suppose that theta 1 was 1 radian. Okay? So suppose that it was 1 radian. We would automatically know the size of S1, that arc. Anybody remember how big that arc would be? If the angle is 1 radian, the arc size is the same as something else. And that's the key that's going to help us. Yeah, Michael?
The radius of the circle?
Yeah, the radius of the circle. So if theta 1 is 1 radian, then by the definition of a radian, we looked at that last time, the size of the arc and the size of the radius match. This is going to be our important fact. Right, so now let's set up a proportion. Let's compare theta 1 to S1 and theta to S. The only reason we can set that proportion up is because arc size and angle size are directly proportional. Right, and let's fill in what we know. All right, so theta 1, we're going to let be 1. And then that would make S1, or the length of the arc, exactly the same as the radius. Okay, and on the other side, you have theta divided by S. We don't have any values for those, so we don't fill them in. And what's the technique we use to normally solve a proportion? We're going to use that technique to actually write our formula out. Yep. Yep, you cross multiply. So we have S times 1. And then we have R times theta. Okay, and that's the formula for the length of an arc. S equals R theta. So S is your arc length. R is your radius. And theta, that's your angle. But your angle has to be in radians. Okay, now sometimes people say that, well, wait a minute, what if theta 1 isn't 1 radian? Well, that doesn't really matter. That was just a starting point to figure out this formula. Just like if I said to you in 1 foot there's 12 inches. Just because you picked 1 foot, that doesn't limit you to converting other things. Okay? Just because we picked 1 radian, that doesn't limit us to using this formula for other things. Okay? It's the same idea.
So like if your angle was pi over 3 radians, we could still use that?
Mm-hmm. You can use that formula for any angle you want. Because remember, this formula, it really just comes from a proportion. So like, let's say instead of doing 1 foot, there's 12 inches. You said, well, in 3 feet, there's 36 inches. Sure, you could set up that proportion too. It's just your numbers aren't reduced. In 3 feet, there's 36 inches. In how many feet are 100 inches? It doesn't really matter what you use on this left side at all, as long as it's a true fact. You could use 1 over 12, 2 over 24, 3 over 36. They're all the same fraction, just different forms of it. Okay? That's the same idea with this using 1 radian. Okay? We could have done 2 radians, but then it would have made it a little more complicated to figure out what S1 would have been. Okay? So I picked 1 radian because it's the easiest. All right, so the first problem, I want to find the length of an arc in a circle that has a radius of 2, and the central angle is going to be pi over 4. Okay, so as a picture, that's what we're looking at. Finding the length of that arc in red. Okay, so first thing, let's just write down the formula. S equals r theta. Okay, and they're asking for the arc length. Which letter in that formula represents arc length? Nick?
S.
Yep, that's S, so that's going to stay as the variable. Okay, my radius. Lasan, what's my radius? 2. And Brian, what's my angle?
Pi over.
Pi over?
4.
Yeah, pi over 4. Okay. Now, what does the angle have to be in? We said that in our formula, we assumed we're working in radians. Did they give me an angle in radians? Yeah. There's no degree on that, so I know it's a radian. Okay, we just have to multiply it out. So it's 2 pi over 4, which reduces to pi over 2. Now I need a label on that. So we just found an arc length. What would make sense for a label here? Marina? Inches, because you found the length of something. You found the length of an arc. You wouldn't put radians on that. Radians is an angular measurement. It's not a measurement of length. Okay? So pi over 2 inches. Any questions on that? All right, let's try one a little different. This time they're giving me the arc length. They're telling me that it's 3 pi feet. And they're giving me a central angle of 60 degrees. They want the radius. Okay, so in this kind of problem, there's 3 variables. They're always going to give you 2, and you'll find the third one, whether it's the radius, the arc length, or the angle. All right, so let's start with our formula again. Andrew, what's the formula for arc length?
The arc length would be so the radius times the angle.
Yep. Yep, angle in radians. That's important. And this time they're asking me to find the radius. Okay, so leave that as your variable. And Silvio, what's my arc length here?
60 degrees.
Could that measure a length?
3 pi.
Yeah, 3 pi. Good. And what did you say the angle was?
60 degrees.
Okay. Any thoughts about that angle? We have to be careful about, Carter.
It's to be radians.
Right, we have to convert that to radians. Does anybody know what that is in radians? If you think, if you get stuck, think of pi as 180. And then think about what you'd have to divide 180 by to make it 60. Yep. It's pi over 3. If you're not sure how you get that, multiply by pi, divide by 180. And then 60 goes into 180 3 times. Okay, now we need to solve for r. Right, so I got to get rid of this pi divided by 3. I can get rid of the pi and the 3 in the same step. What could I do on each side to get rid of the pi and the 3? Yeah.
Multiply by 3 over pi.
Yeah, multiply by the reciprocal, by 3 over pi. And multiply by 3 over pi. So that's gone. What about on the left-hand side? What do I end up with? After I reduce all that.
9.
Yeah, just 9. And somebody else tell me, what should my label be on that? 9. How about Sam? Feet, yeah. A radius, again, that's a length. So go back in your problem and look at your units used for length. 9 feet. Any questions on that? All right, so yeah, again, the idea is S equals R theta. They'll always give you 2 out of the 3, and you're going to find the third one. Okay, so the only one we didn't do this time was solving for theta. Okay, but if you divide each side by r, S divided by r, that would give you theta. All right, so next thing we're going to look at is angular velocity. Anybody ever studied that before? Angular velocity? So it's basically used to measure the speed or the motion of an object that moves in a circular path. Okay, let's see why we need to do that. We already have a way to measure speed. Okay, you can use miles per hour or feet per second, something like that. So why do we need a different way to measure speed when something's spinning in a circle? Does anybody know that? Why can't you measure the speed of something spinning in a circle? And I'm going to show you an example with this disk here. The same way you'd measure the speed of a car going down the highway. Yeah?
Because a point closer to the edge of the circle will be moving faster than a point closer to the inside.
Yes, exactly. So remember your basic formula for distance is distance equals rate times time. So if you take distance, divide by time, you get the rate, the speed. Okay, well, let's look at the 3 points on this circle. Okay, as I rotate it, okay, the one in the center doesn't really move much. Okay, its distance, if it was perfectly in the center, would be 0. Okay, but the one on the outermost edge is moving the most amount of distance. Now they're all doing kind of the revolution there in the same amount of time. Okay, so time is the same for all 3 of those dots, but distance is different. Okay, the one on the outside edge travels the farthest. So if the distance is bigger and the time is the same, then the speed is faster. Okay, so the speed, linear speed of the dot on the outside is actually faster than the dots that are closer to the center, because it's covering more distance in the same amount of time. Okay, so that's the problem. Every point on that disk that's a different distance from the center would be traveling at a different speed. That's kind of confusing. But if we describe the speed in terms of like RPMs or revolutions per minute, they all make the same number of revolutions per minute. Okay, different linear distances, but same number of revolutions. So that's why we use angular velocity.
Basically, you're saying your rate is the same, but their distance is different.
We'll say their angular speed is the same, but their linear speeds would be different. Okay, so angular speed in our book is going to be defined as radians per time unit. They don't specify a time unit, so it could be radians per second, radians per hour. So anytime they ask for angular speed, they want it in radians per time. You can measure angular speed in revolutions. That's RPMs, revolutions per minute. You could also do it in degrees per second or degrees per minute. But our book's looking for radians. And then just to compare that to linear speed, that's the speed of an object that's moving in a straight line. Okay, a lot of times we use feet per second, miles per hour, kilometers per hour, something like that. And the way we'll convert between linear speed and angular speed, or even we'll just practice converting like seconds to years. We'll start out with something basic. We're going to use dimensional analysis. Okay, you've already seen a little bit of that when we convert degrees to radians. I asked you where would degrees have to go to cancel out. So we have it in the top, we have it in the bottom. We're going to do the same thing now with other units, like inches. And so we'll do it with lengths and times and a few other things. Has anybody ever done that before, dimensional analysis? Okay, it makes converting between different units very, very easy. Okay? But you do have to know conversion factors, okay, basic ones. How many seconds in a minute, minutes in an hour, hours in a day, days in a year, feet, inches, how many inches in a foot, how many feet in a mile, things like that. Okay, they should all be conversions that you're familiar with. Okay, let's start with an easy one. Okay, this one's not a rate. Okay, to have a rate, you got to have two units, like miles per hour or dollars per hour, something like that. That's a rate. This is just 3 days. Okay, we're going to convert it to minutes. So let's start with 3 days. I'm just going to make it a fraction. 3 days. Okay, and generally what we'll do is convert it one step at a time. We're not going to jump all the way from days to minutes. We'll go through the units in between. Okay, so what's the next smallest unit than a day? And then we'll have to figure out how many of those are in a day.
Hours.
Hours? Okay, and how many hours in a day?
24.
Okay, so in 24 hours, there's 1 day. So now you have a choice here. You're going to use the 24 and the 1 somehow. You're either going to multiply by 24 over 1 or 1 over 24. Okay? And the way you figure it out, we want days to cancel out because we're trying to get to minutes. Where would days have to go to cancel out? The top or the bottom? What's that? The bottom. Okay. And now look at your equation. In 1 day, there's 24 hours. Okay, so if you stopped there, now you'd have hours. Okay, now we need another conversion. What's the next smallest unit down from an hour?
Minutes.
A minute? And what's our connection between hours and minutes? Josh? 60 minutes equals 1 hour. Okay, where do we want hours to go here? Top or bottom? So bottom. The number associated with hours was 1. The number with minutes is 60. And now look at the units that are left. Minutes and nothing else. Okay, so now just do that calculation out. If you want to reduce, you can beforehand, but actually there's no denominators here to reduce. So you just multiply straight across. Okay, so 3 days is 4,320 minutes. Any question on that? All right, so let's try a rate. Okay, 50 feet per second. I want to convert that to miles per hour. So 50 feet per second means you go 50 feet every 1 second. Okay, so there's two separate things we're going to do kind of in the same time. We're going to change a length unit to miles, and we're going to change our time unit to hours. Okay, it doesn't matter which one we do first. Let's start with feet. Okay, how many feet in 1 mile? Yep.
5,280.
Okay, so 5,280 feet. That's in 1 mile. Where do we want feet to go here? Top or bottom? Bottom. So we have 5,280 feet in 1 mile. If I stopped here, what would be my units? I'd have a speed in what units?
Seconds.
Well, speed has to have a distance as well.
Oh, miles per second.
It'd be miles per second. Okay, that would be miles per second. Okay, next we'll convert seconds to minutes. In 1 second, there's 60, whoops, let's fix that. In 60 seconds, yeah, that's a little off, there's 1 minute. So there goes seconds. Now we have a speed in miles per minute. And one more step to get it into hours. In 60 minutes, that's 1 hour. And then look at your units, minutes, minutes. And now we just look at our final units, make sure everything's good, miles and hours, and multiply straight across. So we have 60 times 60, that's 3,600, times 50, so it's 180,000, divided by just 5,280. Oops, so 180,000. So it's about 34.1 miles per hour. Okay, so sometimes it's kind of surprising when you convert feet per second to miles per hour. So if you're going just 34 miles per hour, that means you're going about 50 feet every second. So that's twice the length of this room every second. So imagine if you're going, like 55, 60, 65 miles an hour, you're covering like 4 of this room in like a second. So it's a lot of distance. Okay, let's try an angular velocity. Okay, we have 200 radians per second, and I want to convert it to revolutions per minute. Okay, so this is an object that's spinning around 200 radians in 1 second. Is that more than 1 revolution or less? What do you think? Think about how many radians in a revolution, or how many radians are equal to 360 degrees? 2 pi, so 6.28. All right, so if you've got 6.28 radians, that's 1 revolution. This is doing 200 radians. So that's a lot more than 1 revolution a second. All right, in fact, that's our conversion we're going to use. In 1 revolution, there's 2 pi radians. Okay, I put radians in the bottom, so we'll cancel radians in the top. And lastly, let's get rid of seconds. Our conversion between seconds and minutes. 60 seconds in 1 minute. So we've got seconds. So it's 200 times 60. And then divide by 2 pi. Divide by 2 divided by pi. 1,910. Let me just double check that. So we had 12,000, I think that's right, divided by pi and divided by 2. Yep. So 1,910 revolutions per minute. That's pretty fast. It's a lot of revolutions per minute.
Are you in the pi button?
I am, yep, I use the pi button.
Because I'm not getting that.
Anybody else get,
Yeah, I got it.
you got that? That's it, yeah, you should get when you use the pi button.
You divide it by 2 and then divide it by 5.
On this calculator, that's the way I did it, yeah. Because I don't have a way to do it nicely like on a graphing one. But yeah, you could just do divide by 2 pi on a graphing calculator. Same thing. All right, so far if we had an angular speed to start, we finished with an angular speed. If we had linear speed, we stayed with linear speed. Well, now we're going to try to make a jump. Okay, we're going to take something that, bless you, is a angular speed to start with, 1,850 revolutions per minute. And I want to basically know if you put that wheel down on the ground, how fast would it go? If it was spinning at that speed, and it stayed spinning at that speed consistently. Okay, so that'll be part B, when we find the linear speed. Okay, let's start with part A. They're just asking us to find the angular speed in radians per second. It's very similar to the example we just did up above, except we're converting back to radians per second from revolutions per minute. Okay, somebody tell me the first conversion I would multiply by. And you have 2 choices here. You can either start dealing with revolutions or you can deal with minutes. Either way. How about Brandon? Tell me, what would you multiply by here?
Could do 1 minute over 60 seconds.
Yep, you could do that. 1 minute. There's 60 seconds, so he took care of the time unit. They wanted it in seconds. And now we have to get revolutions to radians. So how do we do that?
2 pi over 1.
Yeah, it's 2 pi radians in 1 revolution. Look at your units. Radians is in the top, seconds is in the bottom, and multiply it out. Okay, so in the top you should get 11,623, okay, roughly, and divide by 60. Okay, to get 193.7 radians per second. I'm not sure that's going to really help us to do part B, but that's what they wanted for part A. Okay, part B. Find the linear speed of a point right on the edge of this wheel. Okay. Let's go back to what we started with. 1850 revolutions per minute. First thing I'll do is let's change it to seconds. Okay, that's an easy one to do. In 1 minute, 60 seconds. So now you got revolutions per second. We want to get feet per second. So how are we going to change revolutions to feet? Any thoughts here? Yeah?
Okay, so you know your radius up top?
Mhm.
So you can use your radius to find your circumference, and one circumference is equal to one revolution.
Yes, exactly. So one circumference equals one revolution. What's different about this conversion fact is it's a conversion that can change. It depends on the size of the wheel you're working with. All the other conversions we've used so far, they never change. There's always 12 inches in a foot. There's always 60 seconds in a minute. But the circumference in a revolution, that conversion can change. Right, so let's do what Marina just said. Let's find our circumference. And once we have that, that's equivalent to a revolution. So what was our radius? 18 inches. Let's just leave it as 36 pi inches. Okay, now we have a conversion between revolutions and inches. We know in one revolution there is 36 pi inches. Again, for this particular wheel. Only a wheel with an 18-inch radius. Okay, and ultimately we want to get to feet. So now how do we change inches to feet? Josh?
1 foot is 12 inches.
Yep, in 1 foot, 12 inches. Inches, inches. Okay, so if you look at your units, you're left with feet in the top and then seconds in the bottom. Okay, so let's see what we got. So if you had an 18-inch wheel spinning at 1850 RPMs or revolutions per minute, this will tell us the speed in feet per second. So take 1850 times 36 times pi times 1 divided by 60 and then divide by 12. If you want to do it all together, you can do it all together. I don't have an easy way on this calculator. So that's 290 feet per second. So about actually, I guess 291. He didn't really say where to round for these problems, so on the test, I'll make sure I put the directions on where to round. So what do you think? Is that pretty fast? Yeah, that's in the hundreds of miles per hour. That's pretty fast. Maybe a couple hundred. Okay, because we know earlier that, what was it? Something going at 50 feet per second, that was 34 miles an hour. Well, this is almost 6 times that. So it's almost 6 times as fast as 34 miles an hour. So, like I said, in the hundreds of miles per hour. Okay. Any question on that? All right, so that's angular velocity. All right, and last thing, we'll finish up with 6.2. I don't think we're going to get through the whole thing. We'll do part of it, and then whatever we get to, we'll stop. And we'll finish tomorrow. Yeah?
On that last question, there was a lot easier way to do it,
There are different ways, yes.
but you already had the radius, so all you needed to do was convert it just to feet and then multiply.
Yeah, there's some formulas that I'm not showing you that you can use. Because the formulas, I think with the dimensional analysis, for a lot of people, it breaks it down very simple, and they can see units canceling. But there are some shortcuts if you have linear velocity to find angular without going through dimensional analysis. Okay? Your book might show some of them, but I think for a lot of people, they look at the formula and they don't understand why it works. So then if they use it wrong, they don't know they're using it wrong. This, it's pretty easy to see if you do something wrong. If you end up with inches and inches both in the top, something's wrong. You've got to have one in the top, one in the bottom to cancel. So, right, let's take a look at unit circle. Okay, anybody remember from yesterday, what makes something a unit circle? It has to have a special size. What's that size? The what? One more time? Not the radian.
The radius is 1?
The radius, yes. The radius is 1 unit. Okay, so what we're going to do for certain angles, we're going to be able to draw them on this circle. Circle right there. And we're going to be able to sketch that intercepted arc. Okay. On my picture, the intercepted arc, it's that curved red arc on the circle. Okay, once you draw that arc, the arc ends somewhere. For this particular arc, it ends right there, okay, right where that point is. And that point has a coordinate. It's got an x value and it's got a y value. Those x and y values are very important, okay? And they allow us to basically figure out the 6 trig functions of the angle that we had right there. So if you have an angle, and you take that angle, put it in a circle, sketch it, draw the arc, find the end point of the arc. The x and y values on the end point allow you to find the 6 trig functions of that angle. Now I said we can only do it for certain angles. Generally, we're going to stick with doing it for angles that are multiples of 30 or 45. In general, unit circle trig cannot be used to find the 6 trig functions for just any angle. Okay, if we're going to do that, we'll get into more right triangle trig. But generally, unit circle trig is used for multiple angles that are multiples of 30 and 45. You can also extend it to angles that are multiples of 15 with a couple special formulas. Okay, but for now, we'll stick with multiples of 30 and 45. All right, so let's write down the 6 trig functions. Anybody name one of the 6 trigonometric functions? Nick? Tangent, yeah. Tangent's 1. What else? Marina? Sine. Yeah, there's 2.
Cosine?
Cosine. Okay, there's 3. How about the other 3?
Inverse.
So the inverse trig functions, we're going to talk more about those later, but they're not part of the 6 basic ones. But yeah, there is a such thing as inverse trig, and we'll talk more about that later on. So we got sine, cosine, tangent. Anybody know one of the other ones? Yeah?
Secant.
Yep, secant, cosecant, and cotangent. Those are your 6 trig functions. All right, so let's start with the 3 that people said first, sine, cosine, and tangent. These are the 3 that you have buttons for on the calculator. So sine is abbreviated SIN, still pronounced sine. Cosine is abbreviated COS, and tangent, TAN. Now to figure out the sine of an angle, the cosine of an angle, or the tangent of an angle, all you need is either the x-coordinate that I mentioned earlier about the arc length, the y-coordinate, or both. So if you want to know the sine of an angle, you need the y value, okay, of where that endpoint on the arc is. If you want to know the cosine, okay, that's the x value. And if you want tangent, it's y over x. When we talk about right triangle trig, I'll make a connection between this and right triangles, and really these formulas are the same thing. So if you've done SOHCAHTOA, this is just a different way of looking at it, but it's the same idea. Okay, let's look at the next three. Okay, cosecant, abbreviated CSC. What's the connection between the sine and the cosecant? Anybody notice if you had the sine, all you'd have to do to it to get the cosecant? Yeah.
You're basically like dividing by the sine, right? You're dividing 1 by the sine.
Okay, you're taking 1 divided by the sine. And what's that called? When you take him, if you had 5 and then you made it 1/5. A couple names for that.
Inverse?
Inverse. I'm not sure we could call it inverse. You could think of like squaring and square rooting. Those are inverse operations. But this one is a little different when we take and change what's in the numerator and denominator. Yeah, we call this the reciprocal. Okay? Or you could say you flipped it. Okay, it's the reciprocal. So based on that idea, what do you think the formula for secant is going to be? Look at what's across from it in the same row. Yep.
1 over x?
Yep, it's going to be 1 over x. And the formula for cotangent, we're going to follow the same pattern. Flip the tangent, and you get x over y. So those are the 6 formulas that you need to know for unit circle trig. Okay, when we start getting into right triangles, we're going to have things like this. Sine of, say, 42 degrees. This is called the argument. Okay, we've had arguments with all kinds of functions, whether it's a log, a square root. It's basically the thing that you're taking the sine of. Okay? Sine is a function, and it needs a number to get plugged into it. Just like square root. That means nothing, unless you put a number in it, like that. Okay, so it's the number that's plugged into the function. In general, we might not know that number. Okay? In the unit circle trig we're going to do, our goal isn't really to find out what the angle is. Our goal is to find the sine of the angle or the cosine of the angle. Okay? So we might never know how big the angle is. Another way I sometimes explain that is if you met someone on the street, you don't need to know their name to describe things about them. You can describe all kinds of characteristics about them without ever really knowing their name. And that's kind of like what we're doing. Think of the name of the angle as like the size of it. We might never know it. We'll describe some things about it. Okay, for special angles that come up, those are your quadrantal angles. Those are angles that are 0, 90, 180, or 270. Okay, and how do you evaluate a trig function for a given angle? Well, first thing you have to do is find the point that corresponds to the angle. And by corresponds, I mean if you were to draw in the arc, it would be where the terminal side of the angle hits the circumference. That's the point you're looking for. Sometimes the point will be given. Chances are, if it's a more complicated point and we haven't talked about it yet, it'll be provided for you. Eventually, we'll learn how to find the point on our own. Okay? But it might give it to you at first. And then once you have your coordinate, you'll have x, you'll have y. Just plug x and y into the formulas from the previous pages. There were, I think, 6 different formulas. Okay, on a test, I'm not going to ask you to do all 6 in the same problem. I would ask you to probably do one formula per problem. Okay, but in the homework, I'll have you practice all 6. Let's look at our first example. Okay, they give us a coordinate of 0, 1. Now, if you graph that point, kind of like we did in the homework, you could figure out what that angle is. But that's not what they're asking for. Okay, so we'll start off by finding the sine of our angle, cosine of our angle, and the tangent of our angle. Okay, so we've got our point. 0 is x, 1 is y, and now we just have to remember the formula. Let's start with sine. Michael, what's the formula for sine?
Just X. Oh, Y.
Y. Yeah, just y. Okay, what's y in this case?
1.
1. So that's all I want. Sine is 1. Okay, cosine. Brian, what's our formula for cosine?
Just X.
X. So in this case,
0.
0. Okay, and the formula for tangent, Shannon, what's that?
1 over 0.
In this case, 1 over 0, which comes out to what?
We can't reference 0.
Yep, it's undefined. Anybody know what angle we are talking about here? If you were to graph the point 0 and just go up, basically up 1. It is. It's a 90-degree angle. So there's all kinds of connections we can make here, especially graphically. Eventually, we'll be graphing all these functions. Well, if you try to do the tangent of 90, it comes out undefined. And because of that, the graph looks very strange. I'm not going to get into it now, but it does look very strange. There's some asymptotes in the graph. Okay, what's the trig function that's across from sine? Okay, the one you flip. Forget.
Cosecant.
Yep, cosecant. And basically, if you have the 3 on the left, just flip them to get the 3 on the right. What's the reciprocal of 1? 1. Secant. That's the reciprocal of the cosine function. And what's the reciprocal of 0? 1 over 0, which is what? Undefined. Undefined. And cotangent. Yep. The cotangent, what you get when you flip undefined, or really 1 over 0, is 0 over 1, which is 0. So anytime your coordinate has a 0 involved, it's a quadrantal angle. Okay, it's either 0, 90, 180, or 270. And there will be some undefined values. Okay. Sine and cosine, though, you will never see an undefined value. Ever. No matter what your angle is, it'll always be a number. Okay. But some of the other ones, you could see some undefined values. Let's try that one. Okay, so sine is my y value. Okay, Orlando, what's y in this case?
Square root of 3 over 2.
Yep, square root of 3 over 2. Okay, cosine, Taylor, that's my x value. So in this case?
Square root of 1/2.
Yep, 1/2. And my tangent. Okay, tangent is y over x. So we get square root 3 over 2 over 1/2. Now, normally when you have a fraction over a fraction, you flip the 1 in the bottom and multiply, and you can do that if you want. But basically, what's going to cancel out here? The 2's. 2's cancel out. And you're just left with square root 3. If you want to think of it as a fraction, you can. You don't need to. But it might be helpful when you're flipping it to understand that there's a 1 in the bottom. Okay, so my cosecant, I'm going to flip square root 3 over 2. And I get that. But what's wrong with that? Yeah, go ahead.
We can't have a square root in the denominator.
Yeah, we can't leave a square root in the denominator. Anybody remember how you fix that? You do something to the top and bottom?
Square them?
Well, if we square it, we're going to change the number. So we have to multiply basically by 1. Same thing in the top and in the bottom. But I don't want to multiply by 1 over 1. That won't help. Or 2 over 2. That's not going to help.
Square root 3 over square root 3.
Yeah. Square root 3 over square root 3. And you get 2 root 3 over 3. So we will never leave a square root in the bottom. Secant, that one's easy to flip. We just get 2. And anybody think they can give me the final answer for the cotangent flipped and the whole thing fixed? Josh? Good. Square root 3 over 3. So you'd have 1 over root 3, and then you'd have to fix it. I think those are the tougher ones. You got to do a little arithmetic just to get rid of the square root in the bottom. What's different about this one than the last two? What's different there? Yeah.
It's a quadrantal angle.
Okay, so yeah, the key here is they're giving us an angle. The angle isn't helpful though. What do you really need besides the angle? You need the coordinate. So now you've got to figure out the coordinates for 90 degrees. Okay, in general, tonight I'm not going to have you figure out a coordinate other than 0, 90, 180, or 270, but you should be able to figure these out. Okay, you're on a unit circle. What would be the coordinate on the unit circle to get to 90? Yeah?
Any positive coordinate on the y-axis?
Well, it's true. It does have to be positive on the y, but it has to be a certain number if it's going to be on the unit circle. For example, if y was 10, it wouldn't be on the unit circle.
1.
Yeah, y has to be 1. What about x?
0.
0. So the coordinate is 0, 1. We just did that problem. So just look at example 1a for all the answers. The only extra step is figuring out the coordinate. Okay, all your answers are in example 1a. Okay, how about 6 trig functions of 270? What would your coordinate for 270 be? Yeah?
0, -1.
Yeah, it would be 0, -1. Okay, I'll leave the plugging in and going through, I'll leave that part up to you. But that's how you do it. X is 0, y is -1. Fill them in. Okay, pi. Let's just see if we can get the coordinate. Okay, if you're not sure, what's pi the same as in degrees?
180.
It's the same as 180. For some people, they just have an easier time visualizing it. What would be your coordinate for 180? Yep. Good. -1, 0. And again, fill in the 6 formulas. Y, x, y over x, for sine, cosine, tangent, and then flip. Okay, this one, if you're not sure how to do it, you don't like the radians, get rid of them. Right, and what you end up with is Actually, let's reduce that. 7 times 90 is 630. Now that's an angle it's bigger than 1 revolution. What can we do to make that angle smaller? We talked about this. I want an angle that's coterminal with 630, but I want it smaller so I can work with it. Yeah.
Subtract 360?
Yeah, just subtract 360. And it's the same as 270, which is a problem we just did back in example 3. So example 3 and example 5, same problem. All the same answers. And negative 90, again, what I would do, find an angle that's coterminal with it. This time I wouldn't subtract 360. What would I do? I'd add it. It's the same problem again. Negative 90 is the same as positive 270. So just look at example 3. So there's a lot of repeats with these kind of problems. Okay, even though it looks different, it's really the same thing. All right, so the homework is on 324. It's 56 to 61 and 70 to 73, so not very many problems there. And then on page 335, I want you to do 1, 5, and 8. Do what they ask you to do, but also find the 6 trig functions of 1, 5, and 8. Sine, cosine, tangent, secant, cosecant, cotangent. Okay. And try finding the 6 trig functions for these extra 3 as well. 3 pi over 2, 2 pi, and square root 2 over 2.